Understanding a nation as vast and dynamic as China through data presents a unique challenge. How do we make sense of over 1.4 billion people, their economic activities, or their evolving societal trends, especially when a full count is often impossible or impractical? This isn't just about collecting numbers. It's about navigating what we call China's statistical paradox, moving beyond mere descriptions to truly infer what's happening at a national scale. Today, we'll bridge that gap, laying the groundwork for robust statistical thinking using a powerful concept, the Central Limit Theorem. To grasp China's vastness statistically, we first differentiate between a population and a sample. Imagine our population as every single person in China, all 1.4 billion residents. Or if we're studying manufacturing, it could be every single factory in Guangdong province. This is the entire group we're interested in. A sample, on the other hand, is a smaller, manageable subset of that population. For instance, instead of surveying every Chinese citizen, we might survey a carefully selected 2,000 individuals. The challenge is making sure this small sample accurately represents the enormous whole. So, why do we bother with samples? Why not just count everyone or everything in China? The answer is simple: practicality and resources. Conducting a full census on every topic, every year, across China's immense geography and diverse population, is an astronomical undertaking in terms of time, cost, and logistical complexity. Whether it's estimating average household income across all provinces, assessing consumer sentiment towards a new product nationwide, or gauging educational attainment, sampling becomes not just convenient, but absolutely essential for any meaningful and timely analysis. The simplest and most fundamental way to select a sample is through random sampling. Imagine we want to understand the average daily internet usage of urban residents across China. With random sampling, every single urban resident has an equal chance of being selected for our survey. This method is like drawing names from a perfectly mixed hat containing every eligible urban resident. The goal here is to ensure that our sample is as unbiased as possible, providing a miniature, representative snapshot of the larger population, making it a cornerstone for reliable statistical inference. China's diversity, however, often requires more nuanced approaches. Enter stratified sampling. Given the vast economic and cultural differences between, say, a first-tier city like Shanghai and a remote rural village in Gansu, a simple random sample might miss crucial variations. With stratified sampling, we first divide China's population into relevant subgroups or strata, perhaps by province, urban/rural status, or income brackets. Then, we take a random sample from stratum. This ensures that our final sample accurately reflects the proportions and characteristics of these important subdivisions within the broader Chinese population. Another powerful technique, particularly useful for a geographically expansive country like China, is cluster sampling. Imagine trying to survey business owners about their views on new economic policies across numerous industrial zones. Instead of creating a list of every single business owner and randomly selecting from it, which can be logistically complex, we might divide China into clusters, such as specific cities or industrial parks. We then randomly select a few of these clusters and survey eligible business owners within those chosen clusters. This method can be incredibly efficient for large-scale, geographically dispersed studies. While these methods aim for representativeness, one common trap to avoid is convenience sampling. This is where individuals are selected because they are easily accessible. For example, if we wanted to understand nationwide consumer preferences for imported goods in China, and we only surveyed people walking through a single, popular shopping mall in Beijing, our results would be heavily biased. They would likely only represent a specific demographic with disposable income and access to that particular mall, failing to reflect the broader Chinese market. Convenience samples are quick but often lead to unreliable and misleading conclusions about the larger population. So, we've carefully selected a sample, say, 1,000 households in China, and we've calculated their average monthly expenditure. This is descriptive statistics, what we observe in our sample. But the real goal is to make an inference about all Chinese households. How confident can we be that our sample's average expenditure accurately reflects the true average for 1.4 billion people? This jump from what we about a sample to what we can about China's vast population is the heart of inferential thinking. Now, imagine an alternate universe where we could repeatedly take thousands of random samples of, say, 1,000 households across China, each time calculating the average monthly expenditure. If we were to plot all these individual sample means on a graph, what would we see? This hypothetical distribution of sample means is called a sampling distribution. It's not the distribution of individual household expenditures in China, but rather the distribution of the from many, many samples. Understanding this conceptual distribution is key to making valid inferences. And here's where the magic happens, the Central Limit Theorem, or CLT. In simple terms, the CLT states that if we take sufficiently large random samples from population, regardless of its original distribution, the distribution of the will tend to be approximately normally distributed. Think about that for a moment. Even if China's actual household incomes are skewed, the distribution of average incomes from many large samples will look like that familiar bell curve. This theorem is incredibly powerful because it means we don't need to know the exact shape of China's population distribution to make valid inferences. The profound implications of the Central Limit Theorem for understanding China cannot be overstated. Because the sampling distribution of sample means approaches a normal distribution, we can use the well-understood properties of the normal curve to make precise statements about the likelihood of our sample mean being close to the true, unknown population mean for China. This theorem is the theoretical bedrock that allows us to construct confidence intervals and conduct hypothesis tests, giving us a quantifiable measure of certainty when drawing conclusions about the entire Chinese population from a single, well-chosen sample. It's what allows researchers and policymakers to move from we hope to we are confident that. We began with the paradox of understanding an immense and complex nation like China through data. We've journeyed from simply differentiating populations and samples to exploring various sampling methods designed to capture China's diversity, and finally, to the crucial conceptual leap of the sampling distribution and the Central Limit Theorem. This powerful theorem, without delving into complex probability, fundamentally reshapes how we view data. It empowers us to bridge the gap between a small sample and the vast Chinese population, enabling confident, evidence-based understanding. With the CLT, we move beyond just counting, to truly comprehending the statistical heart of China.